Hello everyone. Let's begin today's journey into one of the most fascinating parts of chemistry, ionization of acids and bases. Have you ever wondered why lemon juice tastes sour or why soap feels slippery? It's because of ions released when acids or bases dissolve in water. Ionization is simply the process where molecules break apart in water to form charged particles or ions. For acids, this means releasing hydrogen ions H+ or hydronium ions H3O+. For bases, it's the production of hydroxide ions or -. Remember, the extent of ionization is what separates strong acids and bases from weak ones. A strong acid like hydrochloric acid ionizes completely, while a weak acid like acetic acid only partially ionizes. This distinction is the foundation of our study.
Now let's rewind back to one of the earliest definitions of acids and bases, given by Svante Arrhenius. According to him, acids are substances that produce hydrogen ions in water, while bases are substances that produce hydroxide ions. For example, hydrogen chloride dissolves in water to give H+ ions and chloride ions, written as HCl aqueous gives H+ aqueous plus Cl- aqueous. Similarly, sodium hydroxide produces sodium ions and hydroxide ions. This theory was simple and powerful, but it had limitations. It only worked for aqueous solutions and didn't explain reactions outside water. Yet, it remains the starting point for understanding acid-base chemistry. As chemistry evolved, scientists Brønsted and Lowry widened the definition. They said acids are proton donors, while bases are proton acceptors. This idea introduced the concept of conjugate acid-base pairs. For instance, ammonia reacts with water. NH3 plus H2O gives NH4 plus and OH minus. Here, ammonia accepts a proton, acting as a base, while water donates a proton, acting as an acid. Notice how both conjugate pairs are formed. NH4 plus and NH3, OH minus, and H2O. This theory also explains why water is amphoteric, meaning it can act as both acid and base, depending on the partner. Still, there were cases that didn't fit into Arrhenius or Brønsted-Lowry definitions. So, G.N. Lewis stepped in with an even broader view. According to Lewis, an acid is an electron pair acceptor, and a base is an electron pair donor. This means we don't need to restrict ourselves to protons anymore. A classic example is boron trifluoride combining with ammonia. Boron trifluoride, BF3, accepts a lone pair of electrons from NH3 to form the adduct BF3.NH3. This concept helps explain acid-base behavior even in non-aqueous systems and inorganic reactions, making it a very versatile model. To compare the strengths of acids and bases, chemists introduced ionization constants, K for acids and Kb for bases. The degree of ionization, denoted alpha, tells us what fraction of molecules actually ionize. Strong acids and bases have very high K or Kb values and almost complete ionization, while weak ones have much lower values. Mathematically, Ka equals concentration of H+ multiplied by concentration of A-, divided by the concentration of undissociated acid HA. Similarly, Kb is expressed using OH- concentration. The larger the K or Kb, the stronger the acid or base. This is why hydrochloric acid is far stronger than acetic acid. Let's work through an example together. Suppose we want to calculate the pH of a 0.02 molar solution of hydrofluoric acid, HF. The ionization equilibrium is HF gives H+ plus F-. Using the relation K equals C alpha squared by 1 minus alpha and substituting K as 3.2 into 10 raised to the power -4, we solve for alpha and find the hydrogen ion concentration. Finally, applying pH equals minus log of H+, we get a pH value of around 2.62. This tells us HF is a weak acid. It ionizes only partially, unlike strong acids such as HCl. Always remember to check whether the quadratic approximation is valid in such problems. So, what's the big picture here? Ionization of acids and bases helps us understand the behavior of solutions, predict pH, design buffer systems, and even explain why salts hydrolyze. These principles are applied in industries, from pharmaceuticals to fertilizers, and in everyday lab titrations. To recap, Arrhenius gave us the first water-based definition. Brønsted and Lowry introduced proton transfer and conjugate pairs. Lewis expanded the idea to electron pairs. Finally, ionization constants Ka and Kb give us a measure of acid and base strength. In short, ionization is the language of acid-base chemistry. I hope this session has helped you see how these ideas connect theory with real-world chemistry. In the next lesson, we'll dive into hydrolysis of salts and how it affects the pH of their solutions. See you there.